welcome to the course on biostatistics and design of experiments. We have started talking about factorial designs and then fractional factorial designs. Factorial designs are extremely powerful. We are looking at 3, 4, 5, 6 factors at 2 levels. Then they are also called a 2 power n design, where this 2 indicates the levels, n indicates number of the factors or parameters. So, we can have 3 power n designs and so on actually. Then I started introducing the terminology of fractional factorial design, that means you do a fraction of those factorial design. So, what are the disadvantages of full factorial design? Okay, suppose I take 2 factors A, B, like temperature and pH. So, I can study the main effects of temperature and pH. So, I will be doing 4 experiments, okay. Like yesterday I talked about A at lower level, then A at higher level, B at lower level, B at higher level. So, there are 4 experiments. So, we can study the effects, main effects. We can also study interaction, AB effect, that is called the interaction, that is called AB effect. Okay. Now, let us look at these 3 factors, that is temperature, pH and carbon, that is a 3 factor. So, 2 raised to the power 3 design, 2 raised to the power 3 design, that is 2 into 2 into 2, that is 8 experiments. Okay. So, that will we can study the main effects, that is temperature, pH and carbon. Then we can study 3 two-way interactions, AB, BC, AC, okay, that is 3. In addition, we can also study a 3-way interactions ABC. And yesterday I mentioned generally in systems you will always see a 2-way interaction, like the drug interacting with the race, or drug interacting with the gender, or sometimes temperature interacting with pH, but 3-way interactions are very rare. Okay. So, 3-way interactions are very rare. Now, if we take 4 factors, that is temperature, pH, carbon and nitrogen, we can study each one of these main effects, that is temperature, effect of temperature alone, effect of pH alone, effect of carbon alone, effect of nitrogen alone. In addition, we can also study the 2-way interaction AB, AC, AD, BC, BD, CD and so on. So, there are 6 in number, and then there will be a 3-way interaction ABC, BCD, ACD like that, BCD, that is 4, and then there will be a 4-way interactions ABCD, like that it goes. So, if I am going to have a 5 factors 2 raised to the power 5, we are talking about in terms of 32 experiments, and in addition we are also talking about lot of 3-way and 4-way and 5-way interactions which are redundant actually. So, Box said there tends to be a redundancy in full factorial design because we have excess number of interactions, and generally interactions like 3-way, 4-way, 5-way, 6-way are very rare. 2-way yes, but others are rare. So, we are seeming to be doing too many experiments from that point of view, and also if you do too many experiments it is going to be time consuming, resource consuming. So, why not go into fractional factorial design, that means you do a fraction of the factorial design. So, you take the factorial and then make a fraction, it could be half of that, it could be 1/4 of that and so on actually. So, how do you go about doing it? Yesterday I talked about it. Suppose I have 3 factors A, B, C, I have to do 2 raised to the power 3, okay, that is 8 experiments. So, A is given like this, B is given like this, C is given like this. I also talked about the okay, 2 things, the orthogonality and the symmetry. Okay, that means you have 4 minus means you have 4 plus. If you have say 4 minus means you will have 4 plus. If you have 4 minus means you have 4 plus. Even the interactions will be symmetry, that is why it is called orthogonal. Okay, it is called orthogonal. Okay, this is a very symmetric design. Okay. Now, even the ABC will be symmetric. Now, the question is I have 4 parameters or 4 factors A, B, C, D, A, B, C, D. So, I do not want to do a 2 power 4 experiment, 2 power 4 is 16 experiments, but can I do it in 8 experiments? Okay. That is a half factorial of 2 power 4, okay, half of 2 power 4, that is 8 experiments. So, where do I put my D? So, I put my D here, This is the highest order interaction, and as I have been telling that 3-way interactions are very rare. So, can I put D? That means this will correspond to how you change D. Then what happens? Just like AB, BC, AC, we can also have AD, BD, CD, and if we do that, interestingly they all come like this. Okay, they all come like this. Okay, so each main effect is interacting with the 3-way interaction. Okay, so A is interacting with BCD, B is interacting with ACD, C is interacting with ABD, and these variables are also interacting with each other. Okay, CD interacting with AB, BD interacting with AC, AD interacting with BC, and so on actually. Okay, actually as I said, this is at half of 2 raised to the power 4 design, or 2 4 minus 1 fractional factorial. This tells you number of parameters, this tells you whether it is half or 1/4 and so on. If it is 1/4, I would have put 2 here. Okay, okay, let us go back to another problem. Suppose I have x1, x2, x3, a 2 raised to the power 3 will be 8 experiments, but I do not want to do 8 experiments. So, I am doing only 4 experiments. That is this, how do you write this? 2 raised to the power 3 minus 1 design, because it is half of 2 raised to the power 3. Instead of 8 experiments, I am doing only 4 experiments. Okay, so first to look at this symmetry. Okay, 2 pluses, 2 minuses, the orthogonality, even the first order interactions of 2 pluses, 2 minus. So, this is a good design. So, we have taken this half of 2 raised to the power 3 or 2 raised to the power 3 minus 1 design. Okay. Instead of doing 8 experiments for 3 variables, namely 2 raised to the power 3, we are doing only 4 experiments. Okay. If you look at this and this, okay, there is a confounding between x3 and x1, x2, they are exactly the same. Similarly, if you look at x2 and x1, x3, they are exactly the same. So, there is a confounding between x2 and x1, x3. Similarly, if you look here and there, plus plus, minus minus, minus minus, plus plus. So, there is a confounding between x1 and x2, x3. So, main effects, that is x1, x2, x3 are called main effects, are aliased with 2 factor interactions. Main effects are aliased with 2 factor interactions. So, I am using a new word, alias. Main effects are aliased with. So, there is a confounding of main effect with 2 factor interactions, main effects confounding with. So, this is called a resolution 3 design. Okay, this is called a resolution 3 design. Okay, main effects are confounding with 2 factor interactions. Main effects are confounding with 2 factor interactions, as you can see here, and this is called a resolution 3 design. How do you decide? You look at the number of terms here. So, 3 terms. So, we can call this as resolution 3 design. Main effects are confounding with 2 factor interaction. So, it is okay if you can do this experiment, but if there are any changes, for example, you cannot differentiate whether it is because of a main effect or the 2-way interactions. Do you understand? Okay, for example, if I take this and this, suppose this is temperature, this is pH, this is a carbon amount. Okay, so if I see a change because of carbon amount, I see a change in the yield. I cannot say whether it is because of the carbon amount or because of the 2 factor interaction, that is temperature versus pH, because they are aliased, there is a confounding. Do you understand? So, I will not be able to tell whether it is because of the change in carbon I am seeing some changes in my yield, or is it because of the confounding of x3 with the x1, x2, which is temperature into pH. So, a temperature into pH may also give the same changes. I will not be able to really differentiate. So, because they are confounded, there is an alias, okay, and this is called a resolution 3 design. Generally, resolution 3 designs are not liked because the main effects are, and main effects of course are very useful. So, we do not want, but if the main effects are aliased with 3 factor interactions, then it is okay. Like in our previous problem, we have the main effects aliased with 3 factor interactions, okay, and then but there is an interaction between the 2 factors, okay, 2 factor interaction, 2 factor interaction. Now this design is called a resolution 4 design, because here ABC is equal to D. So this is called a resolution 4 design, this is called a resolution 3 design, because main effects are interacting with 2 factor interaction, 2 factor interaction. Here main effect is confounded with 3 factor okay, 3 factor interactions, okay, whereas in this case the main effects are confounded with 2 factor interactions. So this is resolution 3 design, this is a resolution 4 design. Resolution 4 designs are okay, but resolution 3 designs are not good at all. So in resolution 4 design, what happens? Main effects are confounded with 3-way interactions, I mean 3 factor interactions. So generally 3 factor interactions are very rare scenario. So if there is a change, we can say it is because of the main effects, okay. But then of course there are confounding between the 2-way interactions, So I will not be able to say whether something is because of AB or because of CD, something is because of AC or because of BD. So they are aliasing, so there is a confounding between these two. So in a resolution 4 design, 2 factor interactions are confounded, main effects are confounded with the 3-way interaction, 3 factor interaction, whereas in a resolution 3 design the main effects are confounded with the 2 factor interaction, and resolution 3 design is not a good idea to derive, okay. Okay, let us look at same problem, okay. We looked at this ABC problem. So it is a 2 power 3, so 8 experiments. So what I did was I put a D here, so I made it into a 2 power 4 minus 1 design. Now I want to put a E also, then it becomes 1/4 of 2 power 5, that is 2 power 5 minus 2 here. So if I put E, that is 5 factors, ideally I should be doing 32 experiments, but I want to do only 8 experiments. Instead of doing 32 experiments, I want to do only 8 experiments. So that is 1/4 of 2 power 5 or 2 power 5 minus 2, this is what it is called, 2 power 5 minus 2 design. So I want to put D, I have put D in under ABC, but if I put E under this, the main effect E is confounding with the 2-way interactions, and this is a resolution 3 design as I said before, and this is not generally liked. So if I have 5 factors, okay, this it is not a good idea to do a 1/4 2 power 5 design, because I end up with the some 2-way interactions here, this 2-way factor interacting confounded with the main effect, okay. So it is confounded with the main effect. So this is called a resolution 3 design, whereas the corresponding, if you look here, this is a resolution 4 design. So do you understand this picture and this picture? Okay, this picture and this picture. So instead of doing 32 experiments, I am thinking of doing 1/4 of 32, that is 2 power 5 minus 2, okay. So this is a resolution 3 design, because the main effects are confounded with the 2 factor interactions, whereas here instead of doing with the 4 parameter, instead of doing 2 power 4 16 experiments, I am doing half of 16, that is 2 power 4 minus 1. Here the main effects are confounded with the 3 factors interaction, and this is a resolution 4 design. Generally resolution 4 designs are okay, resolution 3 designs are definitely not okay. Okay, let us go forward further. Let us look at a 6 factors, which, okay, 6 factor is what? 2 raised to the power 6, that means 2 into 2 into 2 into 2 into 2, 64 experiments, okay, but I want to do only 1/4 of that, 16 experiments. So it is 2 power 6 minus 2, so quarter fraction of 2 power 6 is 2 power 6 minus 2 fractional factorial design. Okay, now we have x1, x2, x3, x4. So you start with the 2 full factorial for 2 power 4, because that is 16 experiments. 2 power 4 is 2 into 2 into 2. So you put x1, x2, x3 and x4, and then write all the interactions. You are going to have 2-way interactions, you are also going to have 3-way interactions, x1, x2, x3, x1, x2, x4, x1, x3, x4, x2, x3, x4, x1, x2, x4, okay. So that is how you first make, okay. I want to do only 16 experiments. So what gives me 16 experiments? 2 power 4, that is 4 parameters. So I write the full Now, I have to introduce 2 more variables or parameters. Okay. I have to introduce 2 more effects or variables or parameters in order to make it 6. So, where do I introduce? Do I introduce here? Do I introduce here? Do I introduce here, here, here? So, you have a lot of choices. Okay. Suppose I introduce S6 here and S5 here. So, x5 is equal to x2, x3, x4 and x6 is equal to x1, x2, x3, x4. So, if I multiply x5 by x6, what will happen? I will be left be x1, x2, x2 will become 1, x3, x3 will become 1, x4, x4 will become 1. So, x5, x6 has become x1. This is not desired, as I have been telling always a main effect should not be confounded with two-way interaction. So, the selection of putting here and here is not a good idea. So, I look at some other place. I am looking at this place instead of this and this, I am looking at this place. So, here x1, x2, x3 is x5, x2, x3, x4 is x6. So, when I multiply x5 and x6, what happens? I have x1, x2 into x2 is 1, x3 into x3 is 1, x4 comes here. So, x5, x6 is x1, x4, that is a two-way interaction or two-factor interaction is confounded with another two-factor interaction. So, no problem. Okay, this is allowed. Okay, this is a resolution 4 design. Okay, no problem. Whereas this becomes a resolution 3 design. Okay, so it's a good idea to put your x5 here. It's a good idea to put your s6 here. Do you understand? Do you understand how to go about creating such a design? Okay, I want to have 6 parameters, but I want to do only 16 experiments. So, 16 experiments means it is 2 power 4. For a full factorial, 2 power 4 is 2 into 2 into 2 into 2 will give you 16, 4 parameters x1, x2, x3, x4. So, I write down the whole design. Whole design means I will have a column for x1, column for x2, column for x3, column for x4, and then I will say minus, 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 then I say plus, minus, 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 then I will put minus, plus, minus, minus, like that I will build up. Then how do I generate the two-way interaction? Simple. x1 into x2 means minus minus is plus, plus minus is minus, minus plus is minus, plus plus is plus, minus minus is plus, like that I build. x1 x3 I will multiply x1 into x3, minus minus is plus, like that I build this. Like that I built all the two-way interactions. Then I go to three-way x1, x2, x3. So, minus 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 will give you minus, like that I build up all the three-way. Then finally, I get the four-way interaction. So, this is the entire design table with the interactions, okay, for a 4 parameter. Now, I want to introduce 2 more parameters x5 and x6 because I want to do a 1/4 design of 2 power 6. So, how do I represent 2 power 6 minus 2 or a 1/4 fraction of 2 power 6? The question is, where do I introduce these 2 variables, x5 here and x6 here, or I have so many choices here, here, okay, because a main effect can be always confounded with 3-way interactions, 3 parameter interactions, okay, 3 factor interaction. So, when I do this, x5 is equal to x2, x3, x4 and x6 is equal to x1, x2, x3, x4, what happens? When I multiply x5, x6, I will have x2 into x2 gone 1, x3 into x3 is 1, x4 into x4 1. So, I will be left with x1. So, x5, x6 is confounded with x1. This is a resolution 3 design which is not desired at all, because the main effect is confounded with the 2 factor interaction. So, I need to look at some other place where to put my x5 and x6. So, I think of this place and this place. So, when I do this, okay, when I do that, x5 is equal to x1, x2, x3, s6 is equal to x2, x3, x4. So, when I multiply x5, s6, you will get x1, x2, x2 1, x3, x3 will become 1. So, x1 and x4. So, you have a 2 factors confounded with each other, which is okay. This is a resolution 4 design. Okay. So, this is allowed. So, I can put x5 here, I can put x6 here. What about these 2 places? Can I put x5, x6? Why do not you take this as your homework and try to work out, no, because you have different places where you can put your x5 x6 here and here or here and here. So, I want you to try and see whether you end up with a resolution 3 or a resolution 4 design, whether it is okay to allow. Okay, do you understand how to go about doing this type of approach? Okay, we talked about, we introduced some terminologies like aliased, x5 is aliasing with x1, x2, x3, or x5 is confounded with x1, x2, x3. Okay, so this is confounded with this, and so aliasing. Okay, so we understand the aliasing relationship. So 1, 2, 3 and 5. So this is called a design generator 1, 2, 3, 5 aliased with, okay, 2, 3, 4, 6. So, or we can say 2, 3, 4, 6 or 1, 4, 5, 6. Okay, sorry, yeah, 1, 4, 5, 6. So, the main effects, one is confounded with 2, 3, 5. Okay, one is confounded with 2, 3, 5, which is confounded with 4, 5, 6. Okay, which is confounded with 2, 3, 4, 6. 2 is confounded with 1, 3, 5. 2 is confounded with 3, 4, 6. It is also confounded with 1, 4, 5, 6. 3 is confounded with 1, 2, 5, confounded with 2, 4, 6, 1, 4, 5, 6. Like that we can build up, right. 4 is confounded with 1, 2, 3, 5 or 2, 3, 6 or 1, 5, 6. 5 is confounded with 1, 2, 3 or 2, 3, 4, 6 or 1, 4, 6. And these are the two factor interactions which may be confounded. 1, 2 is confounded with 3, 5, 1, 3 is confounded with 2, 5, 2, 3 is confounded with 1, 5, and so on actually, right. So, this is a very useful relation to build up initially, and then with that we can build up everything. Do you understand? And this is a 4, okay, resolution of design of 4, okay, because these you have 3 plus 1, right, the minimum. Okay, this is how you do the aliasing relationship. Do you understand? So, we take up 1, 2, 3, 5 as I, 2, 3, 4, 6 as I, 1, 4, 5, 6 as equal to I, right here, and then we build up how they are going to be related. 1 will be remaining is 2, 3, 5, 2 will be 3, 4, 6 or 1, 3, 5, like that. Do you understand? And then how to build up the two factor interactions also is given here. Okay. So, as originally we said in the previous picture, when we put here this becomes a resolution 3 design because we have this type of relation. Okay. Now, what is the aliasing relation? I is equal to 2, 3, 4, 5, okay, which is equal to 1, 2, 3, 4, 6, which is equal to 5, 6. Okay, just like in this previous case, it is like this. So, we can build up all the relationship here, no problem, right. So, 2 will be equal to 3, 4, 5 or 2 will be equal to 1, 3, 4, 5, 1, 3, 4, 6, okay, I like that. So, here comes 1 will be equal to 5, 6 or 1 is equal to 2, 3, 4, 6 or is equal to 2, 3, 4, 5 and so on actually, okay. And 2 will be equal to 3, 4, 5, 2 will be equal to 1, 3, 4, 6 or 1, 5, 6. Like that we can build up the I relationship also, that is the aliasing relationship. This is a resolution 3 design because we have 3 minimum comes out to be 3 of that, okay. Okay. Now, the other one where when we selected this and this, okay, x5 is equal to x1, x2, x3, s6 is equal to x2, x3, x4. So, your I is equal to 1, 2, 3, 5 or equal to 2, 3, 4, 6 or equal to 1, 4, 5, 6. Okay. Do you understand? So, 1 will be confounded with 2, 3, 5 or 2, 3, 4, 6 or 4, 5, 6. This is a resolution 4 design because we have a relationship involving the minimum comes out to be 4 parameters. Okay. So, you understand the concept of how to introduce a new parameter if you are doing a fractional factorial design, how to identify the resolution of that design in the factorial and how to look at the aliasing relationship. Okay. So, this x5, x1, x2, this one, this is called a design generator because we can look at all the combinations, right. I is equal to 1, 2, 3, 5, 2, 3, 4, 6, 1, 4, 5, 6 and so on actually, right. So 5 equal to 1 2 3, 6 is equal to 2 3 4, 5 6 is equal to 1 4, like that, no. So this is called a design generator, and as I said, resolution is the shortest word, the generator, this is 4, okay. Whereas if you look at this one, we have x5 s6 is equal to 1. So this is the shortest, no, 1 is equal to 5 6. So obviously resolution 3. Do you understand how to build up these resolutions in this? Okay. Okay, the properties of fractional factorial design, just like your full factorial design or fractional, it has to be balanced, okay. All the pluses in the main effect should be equal to all the minuses, and it should have orthogonal. One is balanced, orthogonal. All the interactions also, the pluses should be equal to minus. So factors occur equal number of times at low and high levels. The interactions also same thing happen. Otherwise, if you do not have like that, if you have more pluses than minus, then it is biased. That means you would like to do more experiments at the higher level than lower level. So it is not a really balanced design, that is not very okay. So sample size for main effect, we will take half of total, sample size for 2 factor interactions 1/4, okay. So this is properties. Once you make your design, check out in case you made any mistake, whether the design is balanced, whether it is orthogonal, whether the resolution is more than 3, and so on actually, okay. You need to understand these properties, okay. Another thing is, for half fractions always alias the new factor with the highest order interaction terms, okay. So the question is, suppose I have a 2 power 4 design, that means 16 experiments, okay, 2 power 4, 16 experiments. Now I want to place 5, the 5th factor, that is that means half of 2 power 5, that is half of 32, that is it is called 2 power 5 minus 1. Do you understand? Where should I place? Okay, the best place of course is here. You cannot place it here because it will become a resolution 3 design, okay. You can try placing, but then you may have problems. So best place is to always alias the new factor with the highest order interaction term here, safe, you are very safe, okay. So x1, x2, x3, x4 is equal to x5. That is how your equation will look like, the I equation will look like, okay, aliasing equation will look like. Do you understand? So write out the full factorial for the first k minus 1 factors for a half fraction, okay. So if I am doing a 2 power 4 half fraction of 2 power 4, I will write a 2 power 3 full factorial design. If I am writing a half, if I am interested in half of 2 power 5, then I will write the 2 power 4 design fully, okay, because half of 2 power 5 is 2 power 4. So I write the 2 power 4 fully, similar, okay. So first I will write the full design for the k minus 1 factor, and then associate the last kth factor into the column, okay, that is the highest order interaction, and put the new variable there. That is always good. So half fractional is very easy to do, okay, it is not very difficult. 1/4 fraction, as I showed in the example, especially if I want to add 2 variables, where to put is a little bit tricky, but when you are doing a half fraction it is very simple. What you do is, you take a design which is number of factors minus 1, okay, and then you put your new variable in the highest order interaction. That is how you do actually. So now you understood what is how to estimate resolution and how to look at the concept of the design generator, okay, the aliasing equation. So resolution 3 design, as I said, has main effect interacting aliased with the 2 order interactions. Resolution 4 design, main effect is aliased or confounded with only 3 order and 3rd order interaction, and 2 factor interactions are aliased with each 2 factor interactions. That means AB will be equal to CD and so on. Resolution 5 design, main effects are aliased with only 4th order interaction, that is 4 factor interaction, and 2 factors are aliased with 3 factor interaction. This is very good resolution 5, but the number of experiments go up. So generally this is okay, resolution 4 design is okay, but this is generally not okay, okay. This is how we go about thinking process. Okay, so let us again come back. Suppose I have 2 3 power minus 1, that means there are 4 runs instead of doing 8 runs, okay, for a 3 factor, instead of doing 8 runs I want to do only 4 runs, that is half of 2 power 3. The design generator is C is equal to AB, okay. So I have A, B, and then I have AB, under that AB column I will put it as C. This is a 3 resolution design, okay. Now let us go to the next one. I have 4 parameters, 4 factors, okay. So I want to make a half of that, that means I want to make half of 16 experiments, 2, 4 minus 1. So I first take the 2 power 3 design, 2 power 3 design is 2 into 2 into 2, that is 8, okay, and then I introduce the new variable D under the column of ABC, okay. This is my design generator, okay, I is equal to ABC D, okay, and this is a resolution 4 design, and design generator is I is equal to ABCD, and this is a 4 design because I have 4 terms here, okay, this is okay. Okay. Now let us go to the next one, 2 power 5, that means 5 parameters. So I have 32 experiments, but I want to do only half of that, so 2 power 5 minus 1, so I am doing only 16 experiments. So I introduce the new variable E under ABCD column. So this is a resolution 5 design, you understand, resolution 5 design. But if I want to do 1/4 of 32 experiments, that is 2 raised to the power 5 minus 2, that is 8 runs, then I end up having D equal to AB, E equal to AC, then that becomes a resolution 3 design. This is not good, okay. If you go for 6 parameter, 2 power 6, maximum will be 2 into 2 into 2 into 2 into 2, okay. Okay, that means 64 experiments. If I want to do half of that, 2 6 minus 1 design, that is 32 experiments. So how do I introduce the in that 32, that is 2 power 5, okay. I introduce F, the 6th parameter under this. So this is a resolution 6 design because you have 6 terms here. If I do 1/4 of that 32 experiment, that is 16 experiments, 2 6 minus 2, what do? I put E as ABC, F as ACD, that is a resolution 4 design because 4 terms. But if I make okay, instead of that, instead of doing 64 experiments, I am doing 8 experiments, 1/8, 2 raised to the power 6 minus 3, then I end up D equal to AB, E equal to AC, F is equal to BC, that is a resolution 3 design. So design generator here is I equal to ABD equal to ACE equal to BCF. This is a resolution 3 design because we have these type of interactions. The main effects are confounded or alleged with 2 factor interactions, okay. That is a resolution. Do you understand how it looks like for a 2 level designs, okay. So we will continue further in the next class on different types of designs. Thank you very much.